Care about roulette? You should care about roulette, though. Well, maybe not. At least care to understand it. Well, it can. The game was ruined. It's not a very good investment strategy. So I think I may have stumbled upon something. So here, this was the original game we played. I'm going to come back in here real quick and put some X's back. Because we're going to play this momentarily.
Is your GoPro on?
It is. It's blinking, yeah. I was actually, something weird. Thank you for checking. Actually, Cheryl, in 244 today, I was running a video of 244, and at some point, it turned itself off. And I turned it back on, and when I turned it back on, it was back to fisheye. So whatever video I recorded in 244 is completely useless now. The damn thing was back too far, and the screen's this big. So thank you for checking in, and if you don't mind, I'm not sure exactly what happened to the thing over the weekend. I guess it got loaded and it's still hung over. So hopefully it behaves throughout the rest of the day, or until it gets its hangover medicine in. So anyway, here's what we did in class. We'll do it again momentarily. Here's what you guys sent me. This is what you guys sent me. You guys sent me some beautiful, beautiful data. All your data is down here. Okay, I don't know. This was the class data we ran originally, I believe. I can't remember now exactly whose is what. And these are the last ones. I know, Jesse, this is yours. But I don't know whose is whose up here. It doesn't matter anyway. What I did was I created a scatter plot. Let's make this a little bigger so it's a little more visible. And what this scatter plot is showing is it shows on the horizontal axis the expectation or the average value of the cases that remained in each game. And on the vertical axis, the corresponding banker's offer for that expectation. Because that's what we were comparing along the way, remember. We would play the game. We never, ever took the deal. We always kept playing. But that meant we got like 8 or 9 deals throughout the course of the game. We got a deal right off the bat after open 6. Then we got another deal after opening 5, and then after opening 4 and 3. And we just kept getting deals from the banker. And we were trying to see what the banker was offering as a function of the expectation. Does that make sense? We're trying to see if there's any kind of a correlation between what he or she or it, I guess it because it was a computer, was offering us based on the value of the cases. So that's what I got so far. Now, it's a little bit busy because you have 8 different data sets, but each collection of symbols is one person. So right down here, you see the folks that have the orange right here. These orange dots right here, they didn't have a whole lot of money in their cases left because they blew the big case right off the bat. Does that make sense? So their expectations are very, very low because of that. You can see like these plus signs and these time signs, those are down here towards the 500,000. There's this one right here that looks like Series 8. So somebody at Series 8, look at the spreads on it. So you can see what the banker's offering versus the expectations. Extraordinarily awesome looking data, but kind of hard to process. Because when I look at that, linear-wise, I mean, the only kind of regressions we did in this class, I don't think fit this very well. I mean, when you look at that, what does that look like to you? If you had to kind of describe the shape of that data, how would you describe it? Think outside the box. Don't use math terms. Use other terms. What does it look like?
That's like somebody sneezed.
Looks like, that's a perfect description. Where's their nose, John?
A mouthful of confetti.
That is exactly what it looks like. It looks like the definition of what chaos theory is. Chaos theory, one of my favorite images of chaos theory. Chaos theory is, you've ever seen Jurassic Park, what's his name? Jeff Goldblum does a great little rough and ready Hollywood description of chaos. One of the greatest things to understand chaos is imagine a cigarette burning in somebody's fingers. Okay, and as that smoke leaves the cigarette, it's kind of pretty much going straight up in the air. Then all of a sudden, all the little atmospheric currents start hitting it, and it starts doing this crazy unwinding and billowing into a smoke cloud. What's going on here? You've got this really tight definition of what's happening up to about $100,000, and then it just sprays like a sneeze. I love that. I was thinking like a trumpet, but I like sneeze better. I think trumpet's like a musical sneeze anyway. So yeah, I mean, so it's kind of hard to predict what the hell is going to happen. It's almost like if you don't have a lot of money, you can kind of predict what the banker's going to, if your expectation isn't very high, you can kind of predict pretty close what the banker's going to do. But if you've got a lot of money in your case, it's really hard to predict within any kind of accuracy what the hell he's going to say. Any other thoughts on this, friends? What do you think? Any other thoughts? Cool? Yeah. So,
You explain it from your standpoint.
Oh, I didn't get anything from this. I kept going.
Okay.
I was going to see if you guys saw anything, because I did 5 more analyses. because I didn't see anything here. This was too spread out to me. I mean, it was too chaotic, and there was too much, like this one especially. I love this one, right? See the little guy right there? I mean, I love this data set. Boop, 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 boop. I mean, it's all over the place. Like, how the hell do you predict what's going? Scott.
Maybe there's key factors on when certain cases are lost. Like maybe, like if you lose the million in the first pick, it automatically sets you down one set of variables.
Hold that thought, friend. Okay, give me like 15 minutes on that. No, it's on video. No, we've got it. Hold that thought. I do think there's something to be said about that, and it goes back to what Cheryl said about data mining. And there's a problem with only having the data sets I have here. Hold that thought. So anyway, I didn't see a whole lot out of this. So I went instead to see, maybe I'm missing something. So what I did now was I slapped all of your data sets together. So essentially, I threw them all on one graph, which if you think about it, is essentially the same graph as this one, except now they're all in one place. I thought maybe the different symbols were throwing me off, but then I said, no, the point is these now because they're all the same particulate size. So I said, okay, so that's not doing it. So then I said, all right, we had a vote about percentages in class on Thursday. Maybe the banker's offering some kind of a percentage of the expectation. Does that make sense? So what I did was I took this same sheet here, which is the expectations and then the banker's offers, and then I made a third column, which is each banker's offer divided by the expectation. So if you look at that cell right there, that means the banker offered you about 32% of what your cases were worth on average. This, about 33% of what your cases were worth. Here about 34, here about 32, here about 26, here about 42, here about 54. So offering, and those percentages are extraordinarily neat and clean. I like them. They're very, very close to full percentages, which makes me think something percentage-wise is going on. Hold that thought. So, but again, this looks like 3 or 4 people sneezing. I mean, that's like, no, at least when we have it here, there's like one nose, right? But here you've got like 3 or 4 people sneezing in unison, which is fun, maybe, if you're into that kind of thing. But at the same time, it again, doesn't show me a great deal. So I was a little bit concerned about that. It's just like, I'm not seeing that either. And you guys stop me. If you're seeing something that I'm not, let me know. We haven't addressed Scott's concern yet, which I love your concern, by the way. I want to come back to that. But we haven't addressed it yet. So then I kept looking, and I said, okay, let's just keep looking. So then I kind of did the same thing. Let me slide this over a little bit. Over. I did, rather than looking at it from an expectation point of view, I said, wait a minute, maybe it has to do with the number of the offer. So in other words, I said, what about his first offer, his second offer, his third? Because what I started noticing, let me give you the rationale for this. What I started noticing back here was as you went from top to bottom, the percentages aren't the same, but the first one in each seemed to be, and Cindy, you were talking about this last time. You actually grabbed us a beautiful model last time of just our data set. But what I did was I was able to compare it with all the data sets. Here's the first offer of the first data set, 32% of expectation, 34% of expectation, 16, hold it off, 25, not 20, 34. And I said to myself, those aren't as varied as the sneeze pattern, right? They're not going up to 82 or down to 6 or something like that. So I said, maybe if, instead of looking at the percentage with respect to what the cases are worth, let's look at the percentage as opposed to which offer it is. First offer, second offer, third offer, fourth offer. Check this out. And this is when I started getting a little bit excited. Look at that. It's starting to be a shape. It's starting to have a shape. And then I said, hell, maybe this is good. Because now, these are all the individual percentages of each step. They're a little bit wider over on the end still. But at least they're clustered a lot more than they were when we were looking at the grand scheme of the expectation. So then I did one more analysis. I was like, well, let's just do the average step. And look at this. Look at that. Now that looks smooth to me. It's got this smooth kind of curviness to it. Does it fit any of our models from this class? Does it look linear? Can we put a best fit line on that? Yeah. We could. Should we? No. I don't think we should. I think if we throw a best fit line, we can do it on Excel, which is kind of nice. Make this a little bigger so you can see it. Okay, so we can come up here to insert, where the hell is it? I always forget this. There we go. Layout, trend line. Okay, so we can There's a line. There's a trend line. I mean, you can put a trend line on there. I just don't think you should. Because what that basically does is it underestimates what he's doing at the first step. It overestimates what he's doing in the middle and underestimates towards the end there. What do you think about quadratic? Why not Cindy? I see Cindy and Sherry are both shaking their head no for quadratic. How come?
There's nothing before his first.
Check it out. Check it out. Let me close this bad boy, get rid of this line. Look at this shape. It's almost like it's got a couple curves in it. Like it's got too many curves for a quadratic. It's got a belly and then this. So it almost seems like it's not quadratic, and it can't be exponential either for that matter, because it's not exponentially rising, unless we're missing something, which I don't think we are. So what I started doing was I just said, well, hell, I have no idea what the banker's doing. Let's see. The only thing I was thinking about was when the banker does his calculation, do you remember on the computer-generated model, it took a couple seconds. Do you remember that? It would say calculating,
Yeah.
and then it would pop out the expectation. That makes me think it's not a simple function. That makes me think it's something convoluted. So I said, well, hell, I got Excel. So I went up to insert the trend lines, and I said, let's just, what do you think, Kelly?
It's the total number of cases divided by the money left. That's what the offer is.
It's the total number of cases.
Divided by the money left in those cases.
It's the total number of cases.
So if you have 10 cases with $10 million left available, you divide that, that's what his offer is.
Wait a minute, hang on a second. Cases divided by dollars doesn't give you dollars, though.
Okay, so if you have 15 cases,
Yes.
and the total amount of money left in all those cases is $1 million.
So you're saying
Divide the
$100,000
total
is his
cases
offer.
by the total amount of money left.
That's his offer.
That's his offer.
Right.
That can't be his offer.
It is his offer.
That's the average.
Did you do it?
No, that's not his offer. His offer is less than that.
You think?
It is. We've proved that already. What you just described, the total number of money left divided by cases is the average value of a case. He doesn't offer that. He offers a fraction of that every time. I mean, that's what this column is right here, Kelly. This column, this column. That's what the expected value of the case is the total sum dollars left divided by cases. That's the average value per case. He never offers anywhere near that. He always offers a fraction of that. That's this is the number you just described. That's what he offers. He never offers that. He offers sometimes 60% of that or 70% of that, but he never actually offers that. Does that make you see what I'm getting at?
Yeah.
And we'll see it again. We're going to run the game again because I want to test my model, but you just described beautifully what an average value of a case is. And if the banker would just offer that, we could all just go home after the first offer. But he never does. Please, God.
I could have sworn that when I did mine this morning that like I ended up getting 400,000, but it came down to like I had like $6 or $5, $100, and 400,000, and his offer was actually higher than the expectation.
That happened a couple times, I think.
Yeah.
Nobody that reported back to me that happened to. Because otherwise you would see, let me close this for a second.
Wrong.
No, I'm not saying you're wrong. I'm saying it hasn't happened yet that I've seen. That doesn't mean it can't happen, but you'll notice the percentages only go up to about 65%. In order for that to happen, it would have to go over the expectation. You see what I'm getting at here, friends? In order for, and I'm not saying it can't happen. I'm just saying I've never seen it happen.
I thought it happened today, Friday, when you did it and you won it. I thought we had.
No. We took what was in our case, which was the $1 million. We
Right.
never made a deal. His offer was, here's our, hang on a second, we had his offer right.
Wait.
Came pretty.
There it is. That's it right there. Here's his offers when we played the game.
Okay.
Here's what the values of our cases were. He never offers the value of the case. He always offers under.
Okay.
So that's what, but we didn't take his deal,
Right.
and that's why we went with $1 million,
Right.
because we kept what was in our case. Now, we had the case which was the 1 in 26 shit that actually happened.
Did that happen to nobody else during this?
Did anyone else get the $1 million? I don't think so. Some folks had a nice case, I think. Or at least one or two nice cases at the end, because you look at some of these values, some are small, and then some are larger. There's a large one right there, right? 478,000, so they must have been close to the 1 million right there. And then we had 300,000, 2,500. 300,000. It's about widely variant, which is great. But you'll notice that he never, there's close, right? That one's close to the value of the average, but it's never equal. It's never going to be equal. And I say never only because I've never seen it. I have no rule for his model yet. That's the whole point of the data, is trying to come up with a rule for his model. I'm glad that I have more data waiting for me in email, which is I can drop that in. But we can also develop the model right now and test it, see if we can make it match what he's saying, which I'm very excited. Yes, I'm very excited. Very excited. So anyway, back to this. So I just decided to start messing around with it a little bit. I said, what the hell? Let's see what kind of trend lines we can throw on here. So linear we didn't like. Exponential, let me slide it over a little bit so you can see what's going on there. So exponential, again, it's not bad. Exponential's not bad. I wouldn't say it's a terrible fit. So there's one model. So let's test this. Let's put the equation on the chart. So let's write down these models and let's see which ones work. So bankers, models, potential. And Sydney, I'm kind of preferential to the exponential model because it was the first one that you thought of in class on Thursday.
Well, I just ran what I'm not sure.
Oh, this is going to have a different base to whatever. You ran the XPreg on your TI?
Yeah,
Absolutely.
The cubic.
Oh, we're getting there. Because this actually has super polynomial functions too, which is pretty sweet, yeah. But I like this one. So here's one equation. Let's write this one down. And what we're going to do is we're going to use our TIs and we're going to play the game after the break, and we're going to see if any of these models seem to predict what the banker is going to do. See what I'm getting here, friends? So y equals 0.1781 e to the, is that 0.1364x? I think it is. I'm going to make that bigger to make sure I can see, make sure I get those numbers right. Yeah, that was good. So what's cool about this one, and for all of these, x is going to be the offer number, and y is going to be the offer amount. Oh no, offer percentage. So percent of expectation. Yeah, I'm curious. I'm very, very curious to see what, if any of these do a pretty good job of predicting. So when I say, let me slide this over here so you guys can see it later. So when I say offer number, his first offer, which would be after, I mean, everybody has to do at least one offer, right? You have to do at least one offer because the offer, the game only starts after you open like 5 or 6 cases. So then he's going to offer you the first offer. So you have to get at least that far. You can't walk with the case that you've got because it's not on the board yet. But you don't have to go all the way to offer number 9 either. You don't have to go all the way to offer number 9 or whatever it is, offer number, I guess it's number 9. You have to stop. Now, this doesn't answer that question as to whether you should stop or not. It's only giving you a percentage. And remember, that percentage could be the percentage of 5 cents. You know, he's offered you 100% of 5 cents. Yes, that's fantastic. And this goes back to what you guys were saying too about going over 100%. If you get down to the point where you're arguing between a penny and 5 cents, he might offer you $10 because he feels bad. So that would be well over 100%, but I have no idea, and that goes back to your question, Scott, as to the amount of the case and as the cases leave, which we're going to see why that might be a trickier one to answer. We'll come back to that, though. I love that.
Well, another one is I was wondering, like, what are the probabilities? I'm sure there probably is, but
yes.
Like a website that actually says what's the likeliness of like a given case with a given amount of money?
Well, it's 1 in 26.
No, but what I'm saying though is there a trend in how they do it? Like, does number 5?
Historically,
yeah,
how they assign the amount. Oh,
yeah.
You have to have the database of all the results of the game, which I would bet exists somewhere, because some dork like me would have been collecting it. I just haven't thought of it right now. Yes. It has to exist. The database has to exist. I just don't know where it would be. Because I know it's like Powerball. As you look at Powerball, on the website, they have historical games and the tickets that have been back for 10 and 20 years, which ones have hit. And you can, what's cool about that is testing those tickets. It's purely random. It's beautiful to watch. It's a beautiful thing to check. So, fair enough? Good? So that's one model. There's one model, but let's just take a look. Now, Sydney, I love what you said. She was running the data through her TI, and she said there's a cubic model. We didn't talk about cubic models in this class because I sensed you guys were getting bored of the modeling. You didn't like it so much. You didn't like it. Linear, exponential, quadratic. You're like, yes, I've had enough. Let's do something else. But now we're actually kind of like, we see the point, we're like, this is kind of fun. Like we can see which shape fits. So let me delete this one off real quick. Okay, back to trend line options. Okay, we don't like linear. That one's called a logarithmic model. Logarithms are fun. Well, I think they're fun. You might hate them, that's okay. logs are really good when you have extraordinarily disparate data. I was thinking about logs originally when I saw the original data going like this, because I thought to myself, if I can measure the variation appears to be increasing, sneeze like it, or don't worry about it, otherwise exponentially. And logarithms are a way of taming exponential growth. In case you were wondering how much of a geek I am, this should cement the deal for you. My son wanted a solar system model in his room. He's 5, remember, kids. He's awesome, totally awesome. I was like, that's awesome, Max, but we can't. It's got to be to scale. You know, because I don't teach you the wrong stuff. You can't have you can't have Pluto like right around the corner from Mars. I mean, you have to have an appreciation. He's looking at me like, Dad, I'm 5. You know, like I don't. So I settled on the logarithms of the distances. So in other words, suppose, let's make up some nice numbers. Suppose that Mars is 10 miles, Mercury is 10 miles from the sun. And suppose that Venus is 100 miles from the sun. And suppose that Earth is 1,000 miles from the sun. And suppose that Mars is 10,000 miles from the sun. I'm making these numbers up because they're nice. I mean, obviously they're not true, clearly. So you'd have, in order to make it to scale, you'd have to have Mars 1,000 times further away from the sun, which is his like in his room, 1,000 times further away than Mercury is. Well, what logarithms say is, no, don't use the actual number, use the exponent that you have to raise 10 to. So in other words, you would put Mercury 1 unit away, Venus 2 units away, Earth 3 units away, and Mars 4 units away, because 10 is 10 to the first, 100 is 10 squared, 1,000 is 10 cubed, and 10,000 is 10 to the fourth. So it's called logarithmic graph. Does that kind of make sense? But it doesn't make sense for our data at all, because our data isn't shaped like that. So obviously there's no powers of 10 thing going on up there. So that will not be throw logarithms out. And based on your faces, I'm glad we didn't talk about logarithms more in this class.
No, but I want to see the solar system when it's done.
Well, it keeps falling down because I keep smashing my head into Jupiter when I go through his room. The damn thing, I hung them too low. I did the scaling great. Now the freaking things are hanging so low, I smash them with my hand. Anyway, let's go to power. We'll come back to polynomial because that's what Cindy was talking about. Power kind of looks like logarithmic, and the reason power doesn't work. Power is a model I was going to do in this class with you guys, and I decided against it. What it does is, it allows, okay, so quadratic usually has an x squared. I mean, well, that's what makes it a quadratic, it's an x squared. Cubic has an x cubed. Quartic has an x to the fourth. Linear is x to the first. They jump by integers, 1, 2, 3, 4, 5. Power allows you to find numbers between those that would fit. So for example, you might have an x to the 1.5 power, which doesn't have a clever name like linear or quadratic. It's like halfway between linear and quadratic. It doesn't have so what a power function is it lets that variable be up top in the, or let the exponent be itself a variable, and it finds the best fit variable. That doesn't fit very well, unfortunately. That's not a very good fit because it's looking like the logarithmic. So I skipped over power. Moving average is a bitchin' one. Some of you guys taking 243? A couple of you maybe taking 243, yeah-ish. Yeah, 243 we'll talk about moving averages. They're very, very handy ways, crappy ways of describing this data because of the periods. It looks like it fits it pretty well, but there's no justification for using it. You'll see why momentarily. So then I was stuck with polynomial. So that would be a quadratic model right there. That's a quadratic model. Okay, that fits kind of nicely, kind of like the exponential model, huh? I say we keep that one on board too. So that's y equals 0.0069x squared minus 0.0168x plus 0.2419. Let's keep him on board.
What was the first one we did?
This was exponential. Excellent question, Janae. This is exponential. This is quadratic. But what's wicked cool about this, if you bump down, well, you can't bump down because it'd be linear. You can bump this up. That's now the cubic model. So in other words, this is now a cubic equation. This is a fourth power equation, a quartic model. that's a 5th power, and that's a 6th power. Now, it won't let you go any higher than 6th in Excel, which means if you have better software, you can go as high as you want. But look at that 6th power model. It's actually following the curves of the differences in the percentages. See what I'm getting at there, friends? I think you play with this one too. Just because it has all these goofy inflections, like it traps that inflection right there, and then this cool inflection here. Almost a nod to when the banker offers you a higher percentage at the very last, when you're down to just your case and one more case, he tends to bump up his offer right then. We saw one on here that was almost offered 100% of the case. You see what I'm getting at? So every time, and this is the only thing you have to remember about polynomial curve fitting, every time you add the order is just the size of the exponent. So that means there's an x to the 6th somewhere, and you can see it right there in the coefficients. Every time you add another exponent, like 5 to 6 to 6 to 7, the curves curve potentially one more time. So a linear doesn't curve at all. A quadratic curves once. A cubic can curve twice. A quartic can curve 3 times. A quintic can curve 4 times. And a, whatever you call this, a hexic can curve 5 times.